Friends, welcome to my YouTube channel. Dhanesh here. In the last video, we were discussing about chi-square test and exploratory data analysis. In this video, I am going to discuss about degree of freedom. Let's start. This is a nice quote from Sir Isaac Newton. If I have been further than others, it's by standing upon the shoulders of giants. Let's continue with degree of freedom. Let's start with the statistical definition for degree of freedom. Degree of freedom are the number of independent values that a statistical analysis can estimate. It's simple. The degree of freedom is equal your sample size. Degree of freedom equal your sample size minus the number of parameters you need to calculate using an analysis. It's always a positive whole number. These definitions are pretty simple. It is equal to the number of, it is equal to the sample size minus the number of parameters you need to calculate. We use degree of freedom in many contexts throughout statistics, including hypothesis tests, probability distribution, and regression analysis. Fine. This is a simple introduction to degree of freedom. I am giving a simple example for degree of freedom so that you will get more clarity on degree of freedom. Let us assume that you have 7 shirts and need to use 7 days in a week. So total number of shirts is 7. You have 7 shirts and you have to use it in 7 days in a week. So on Sunday you can have you have 7 shirts. You have 7 choices. Out of 7 you can choose. But Monday it becomes 6. It's coming down. Tuesday it becomes 5. And Wednesday it again decreases, and finally Saturday you have no other choice. You have only 1 shirt, because here you have no other choice. This is the concept, because here you don't have any degree of freedom. See, here you have 1 degree of freedom. Here you have 0 degree of freedom. I can tell you like this. That is n minus 1, the number of parameters. Here the number of parameters is 1. That's the definition. Here the sample size minus the number of parameters. Here the number of parameters is 1 because you are using 1 shirt per day. This is the number of parameters. So here you have, the sample size is 1 and the number of parameters is 1. That is 1 minus 1 is 0. Your degree of freedom is 0. On Friday, you have the, sample size is 2 and the number of parameters is 1. So you have 1 degree of freedom. Here you have no other choice. So you understood. That's the concept of degree of freedom. Next, I am discussing the math behind the degree of freedom. The formula for degree of freedom equals the size of the data minus sample data minus 1, as we discussed. So degree of freedom is equal to n minus 1, where n is the sample size and df is the degree of freedom. Simple. It's a very easy concept. See, this table is a very interesting, nice table. Why I am telling is I am going to discuss about the degree of freedoms of different tests. You have, when we discuss about exploratory data analysis, EDA, for a bivariant analysis, there is numerical to numerical analysis, right? There is the variance can be both numerical, both categorical, and one numerical and categorical. If both numerical, you will go for correlation coefficient. If both are categorical, you will go for chi-square test. And if one is numerical and another is categorical, you have t-test, z-test, and Anova. Am I right? So I am going the degree of freedoms for all these different tests, how it would be. See, different tests and the degree of freedom. For example, for a t-test, t-test. If you are we have separate videos for t-test, you can watch that. For chi-square test, z-test, Anova, we have videos in the playlist. Please watch it. See, for one sample t-test, the degree of freedom is n minus 1. Very important. For two sample t-test, it's also known as independent t-test. The degree of freedom is n minus 2. So one sample t-test, this is also t-test. Two sample t-test or independent t-test, it is n minus 2. For chi-square test, there are two options. One is the goodness of fit, and chi-square test when there is contingency table is there. See, when there is goodness of fit, it's simple n minus 1. When there is contingency table, this is r minus 1 into c minus 1. R is the number of rows in the table and c is the number of columns in the table. If you want to get more clarity, you watch the video for chi-square test under the playlist, statistics, or even under the playlist feature engineering is also it's available. So under the playlist statistics, you have the video on chi-square test. It's a very interesting concept that is used for, when both the variables are categorical variables, we go for chi-square test. So when there is contingency table, the degree of freedom is calculated by r minus 1 into c minus 1, where r is the number of rows and c is the number of columns. For Anova test, between groups, it's number of groups minus 1. For Anova test within groups, you need to use this formula, number of subjects minus number of groups minus 1. For correlation means there should be two variables, right? Bivariant means there should be, so then the degree of freedom is n minus 2. This is a very nice table. You will get all the, degree of freedom for different types of tests. That's why I have given this table as well, because this gives very important table where you should use these, tests for what type of analysis. When both of them are numerical, you will use correlation coefficient. Both of them are categorical, you will use chi-square test. Numerical categorical, you will use t-test, z-test, and Anova. So when these tests you are performing, this is the degree of freedom. So that's all about degree of freedom. Thanks for watching. Please like, share, and subscribe. Thanks a lot.